Welcome to class. How are you feeling? How was your weekend? Anybody encounter anything pertinent to artificial intelligence over the weekend? I don't know why you would.
My computer reached sentience.
Awesome! I knew that was going to happen. Okay, I've been waiting for that. My 8-year-old daughter whooped me at chess, further proving I can build things smarter than myself. I played her again, she whooped me again, 5 times in a row. My 8-year-old creamed me at chess. I thought I was okay. And then, so I'm really confused because my wife is way better than me at chess, so I turned around and played her because my daughter beat her at chess. And then I was going to make her feel better by losing to her, and I started to beat her, and then I lost on purpose.
Intelligence at work.
I hope she doesn't watch that. No, it's recorded. I never admitted that. I didn't actually lose on purpose. I just made one bad move on purpose, and then after that I was hosed. Okay, anyway, Wildcats out of the bag there. But yes, I now know for sure it's possible to make things smarter than you are, which is weird and psychologically strange. Speaking of which, could you, using your brain, find the optimal path in some random terrain map?
Might take a while.
Well, yeah, you could, but man, what a pain, right? I don't know if this thing's, can we really say this thing's smart, or is it just more persistent than you? Well,
Persistent.
even if it's more persistent, it's still more capable. So what is the point of intelligence? Is it not smart? Is it not capability? So here's a philosophical question. Which would you rather do? Accomplish great things or be a member of Mensa? No, not trying to bag on Mensa, by the way, but so Mensa is this club of people who say they're really smart, right? So what if you're really smart, but you never do anything with yourself, with your brain? You've proven you have the potential, and then you never live up to it. Isn't that just sad? Have you ever heard the statement, I would rather have someone say, why was no statue, wait. I'd rather have someone say, why was no statue built of me, than why was a statue built of me, right? Well, same thing goes for intelligence. Are you really intelligent if you don't do anything with it? I don't know, maybe you are. But I'm going to claim these things really are intelligent because they solve that problem. And there's no way anybody in here solved that problem without the aid of a computer. I mean, you can, but why? You'd be so slow. You'd take till next Thursday at least. And anyway, speaking of which, how's your assignment going? Let's do some Q&A today because I kind of want to dedicate class to helping make sure you all have done this assignment.
Can you explain how maps work, because we did not do that in our assignments?
I can. Okay. So, what is a set and what is a map? Okay, let's ask you guys. Surely somebody has covered this in Paradigms. Anybody have me for Paradigms? Do you know what a set is?
Nope.
Dang it! No! Ah.
Hey, I know how to do a deep copy though.
Awesome.
Yeah,
You know
make sure
what?
we knew that.
I didn't cover sets or maps in my Paradigms class either, so I guess I have to now. Let's do a tree set. Do you know what a balanced tree is? Did you ever study balanced trees, maybe in Foundations 2? Algorithms? Algorithms, okay. Well, that comes after Paradigms, not a prerequisite to this class. I will draw a tree for you. As everybody knows, trees start in the sky and grow downward. That is true in computer science. I don't know why we always start at the top and we grow downward.
We have to count the roots.
Yeah, they should really be called roots since we were in it together.
Yeah, we should call them roots instead. See, selection, flip. There. Now it's a tree.
It's upside down though.
But now it's upside down, which is clearly wrong. So we're going to flip it again. This is a tree. Trees are roots. Okay. The idea here is you allocate an object at every junction. We're going to call these nodes because that's what we always call them, nodes. And there's two kinds of nodes. These are, let's see, I will color my interior nodes blue, whoa, or the whole tree. That's not an interior node. Okay, I'm going to color 1 pi of each of my interior nodes blue, and I will color the leaf nodes yellow. Can that show up? The contrast is totally weird on these projectors. Okay, blue is interior, yellow is leaf. That makes sense, right? Leaves are at the ends of the branches. Okay. The whole point of a tree is we're going to put stuff in it. And I can't remember, do you put things in all the nodes or just at the leaves?
All the nodes.
You do it all the nodes. That's right, you do. So there's a whole lot of different types of balanced trees. The most popular are AVL trees and red-black trees. And I'm not going to describe the AVL or red-black algorithms to you, but suffice it to say that when you add a new node to your tree, what happens is, here comes a new node, and I'm going to put it in my tree. I'm going to start right here, and I'm going to say, is this one greater or less than the node at this point? And we'll say it's less than. Is it greater or less than this node? We'll say it's greater than. Is it greater or less than the node at this one? We'll say greater than. And so is it greater or less than this leaf? We'll say less than, and it goes right here. And then we add it to the tree. I have now added it to the tree. But there's a problem. This tree's not very balanced because it's looking really long down here and kind of short up here. Tangentially, I have a tree in my front yard that has one branch that extends way over. And I know one of these days there's going to be an ice storm, and it's going to get heavy, and it's going to rip off, and it's going to break my tree, and I'm going to be really sad. The problem is I can't reach it. It's way up there. What should I do?
Get a ladder.
One of those chainsaws.
I looked into it. The ladder I would need would cost about $500 because it's way up there. But
There's somewhere that makes ladders.
long story short, it's a hardware problem. I don't know what to do. I'm a software guy.
Is it gonna land on anything? Is it something?
Yeah, it's hanging right over my driveway, so I won't be able to get out. Well, drag it out of the way.
Put a chainsaw on a drum. Quad drum.
I don't know. It's the coolest branch, though. It gives shade to my entire front side of my house. So I don't want to lose it. I just don't know what to do about it.
Just don't park under it if it falls. You make sure you have a big rope and a winch and drag it out of the way.
Park behind it. Park
Yeah.
behind where it would fall.
Move the whole tree.
I could do that. Move the tree.
Move your driveway. How about that?
Move my driveway. Maybe I'll climb up there and get a rope and tie it to that. Okay, sorry, off topic. Moving on. This tree is out of balance too, like the tree in front of my yard. What are we going to do? Well, there's algorithms. Red-black does it one way, AVL does it another way, but you kind of shift the nodes around, but you preserve their order. Meaning, you don't want to get them out of order, because that would mess up the whole point, but still shift them around until the tree's more balanced. I invented my own balancing algorithm that I like better than red-black and AVL, and it works just as fine. And I did a whole bunch of empirical testing, and mine is even faster than AVL, so I claim the Gashler bet tree balancing algorithm is the best. But I don't have it in all the programming paradigms textbooks, so oh well. So I don't even know why I told you about that. I just like bragging because I think highly of myself. Now, where was I? What I'm trying to say is, now suppose I wanted to ask the question, is there a number 7 in this tree? What do I have to do? Well, you take a 7, and you say, is 7 greater or less than this node? And we'll say greater than. Is 7 greater or less than this one? Less than. Is 7 greater or less than this one? It's the same as. Oh, well, there is a 7 in the tree. We just found it, right? Or we'll get to the end and we'll find out it's not there. Either way, we will answer the question, is there a 7 in this tree? How long will that take? On average. Let's say there are n nodes in this tree, where n is some ridiculously large number, like 100 gazillion. Long n.
It's log 2 base. Or log
Yeah,
base
it'll be log base 2 of 100 gazillion, or log base 2 of whatever n is on average, if the tree is balanced. If the tree's unbalanced, then it depends if we're lucky or not. And usually you're not lucky because by virtue of it being unbalanced, most of the mass is in the unbalanced portion. So it's kind of important to keep your trees balanced, and that's not your job. That's the job of the Java tree set class. But as you can see, you can find any node in it in log n time, which is really fast. Now you know the theory behind a tree, and you don't even care because you're just going to use the Java tree set class. Except, in fact, you're not going to use the Java tree set class because, as it happens, the Java tree set class is pathetically written, and it contains no find method.
It does. It has a contain no
Okay. If you're going to write a set class, write a find method. That's kind of what sets are really good at, is finding stuff in it. And yet the Java tree set class has no find method. So if you use tree set, you are hosed for this assignment because this assignment relies on find. So if you did, sorry.
I did with tree sets.
You did it with tree sets and you made it work?
Yeah.
Why do you need a find
I did it
for
with a tree
this?
set.
Well, let's get to that.
You told us in the example to use the tree sets. So I thought we had, or not had to.
Ah.
I thought it was recommended to us
You know
to
what?
use it.
For the closed list, all you need to know is if it's contained in it.
Okay, well then let's ask this question.
It's the updating nodes, which is hard because you can't pull a node out to change the cost when the cost is lower.
This is the line right
Right
here
there,
that's
yeah.
giving everybody trouble.
Yeah, I cheated.
Of you who did that, what'd you do?
I did it.
Floor.
Yeah, it's the floor function for tree set. It returns the element that's equal to the one I'm looking for, or the next one.
There is a Boolean method called contains that just returns true if that object is.
Right, but it doesn't return the object.
But you don't
I
need
think
to,
you
you
need
don't
the
need to
object.
return the object. All you need to do is check if it's in there or not.
But you have to update it.
You have to update the cost. Or you could do the super cheap way like I did and do a double-sided
Right, okay, so
array.
there's a
Called
floor.
cost array.
There's a floor, you're good.
And a ceiling.
And the ceiling. Okay,
Can
I retract my comment, but yeah, I'll give you a chance to talk. Okay, go ahead.
So I actually spent almost all semester doing pathfinding with this stuff, and it took me a long time to figure this out, but when a node is placed in your been there list,
Okay.
you never have to change it again. Because if your algorithm is correct, because the first time you get to it, it should be the fastest path to get there.
That
The first
is
time you examine
true
it.
in breadth first search. It's not necessarily true in uniform cost search.
Oh, but in
And I
this,
will show you why.
algorithm though, in breadth first search,
In breadth first search, that is true.
yeah.
Yes. Okay. All right. Let me tell you how to use floor or seal to implement find. So first of all, what does this do? Floor returns the greatest element in the set less than or equal to the given element. In other words, if you're looking for a 7, it might return a 6. Right?
That's why you use contains first. You check if it contains.
First check if it contains, then use floor, then you're good. Or use floor and then check if it's equal, and then you found it.
Yeah, we kind of some work around that.
Okay, I'm going to remove all my exclamation points because even though it doesn't have a find method,
They still need to find that room.
It still needs one.
you can hack
It should be
it.
nice.
And the way to hack it is call contains and then call floor. And if it contains it, then floor is the same as find.
Wait, can you like write like a small like example of this? Because I'm not entirely following.
Okay, fair enough. Okay, I retract my position. I thought there was no find method. There is something like that.
It's the find method.
I'm going to say import java.util.reset. Is it there?
Star.
Never! I will be explicit.
Import Java.star.
Okay. Very good. Somewhere in here, we're gonna have a tree set of element type, what, my state. By the way, you don't have to name it my state just because my pseudocode did. I know everybody will, and that's fine. Just be aware that you didn't have to. In case you thought that was important, not important. My set. Okay. Now, cost search. Okay, essentially here we're going to say my set dot insert new my state, and assume this constructor automatically sets it at 100, 100, or maybe I'll be explicit there. And then we're going to say while my set dot size is more than 0. Wait a minute, what am I doing?
Don't know.
I'm somehow using my set as a priority queue, which is confusing me, because I was confused. We're going to rename this bin there. Then in the foo constructor, we're going to say bin there equals new tree set of my state. Am I on the right path? Come on, guys, you gotta pay attention. I'm not just doing your assignment for it, yeah. You gotta help me out, tell me where I'm messing up. Okay, I've made a tree set here, and now every time I find one, I need to ask the question, have I been here before? Right? Let's do that here. Boolean, have I been here before? Hibba-hub. Hip-hub, which stands for have I been here before. Now I want to answer this question. How am I going to answer it? I'm going to say if been there dot I have to say, let's see, my state temp equals new my state x comma y. Do you see why I'm making a temporary my state here? Because I'm going to have to ask the question, does bin there contains something like unto temp? And if it does not, I can say I have definitely never been here before. Right? Now the problem is, if it does contain it, I actually need to get it for some other purpose. So I will now try to get it by saying my state it equals bin there dot floor temp. Okay.
Shouldn't that be in like an else if or something? Oh.
I'm going to claim now at this moment I can be certain that it refers to the object in bin there, my tree set, that has a x and y position equivalent to temp. Because I know it contains something like that, because I just asked that question. And floor will return the greatest element that is less than or equal to the element I passed in, which will be the one itself, because I know it's there. So it now refers to the element from my state that I wanted to get. Assuming I did that right, does anybody think I made a mistake?
Could you repeat that?
Okay. Let's see. Yeah, let me state it in words. First thing I'm doing is I'm creating a state that represents the state I'm looking for. So temp is not the state I want, but it does have the right x and y value here, right? So it doesn't have the right cost, it doesn't have whatever I'm looking for, it doesn't know who the parent is. Those are the kinds of things I'm looking for because I'm going to update them. But I'm making a temporary state here so I can go find out, have I been here before, and if so, I want that state that represents my having been here before. I make this temporary variable, and now I ask the question, does my set contain one like unto temp? If it does, I know it's in there. How do I get it? Floor is the answer. Floor will get it for you. The problem is, if it's not there, Floor will give you something else. That could be awfully confusing. So you probably want to call contains first to find out if you're going to get the right one. And if you do, then Floor will give you the one that you're searching for. I think we're good. Okay.
If you just put it right back into the set, it'll overwrite the one that's already in there.
If you were to insert one in the set, yes, it would overwrite the one that's already there.
How does contains check if they're the same, if it's in there?
Ah, so does it use a comparator or do you override the compare method? I always get those two confused.
You override the compare method of the comparator. No, you just override the comparator.
You just override the compare method? Okay.
I did
But
that.
you can do that by passing a comparator object.
Yeah, you can do it either way.
So, oh, okay.
So if it
There's two
returns
ways to
zero,
do the
then
comparison.
It returns
Let's go
true.
back to here.
Is that how it works? I did the comparator, but I don't know which. I guess is it when it returns
So here's my
zero?
myState method. You notice I didn't overwrite the comparator for you. That's because that's a Java detail and I'm expecting you to deal with that. Essentially, you're going to overwrite the compare method. So your code will look kind of like this. You'll come here and you'll say, now is there do all objects have a compare method or do I have to implement some
All objects.
all objects? So I just have to say Boolean
Or
compare.
no, sorry, you have to implement it actually in Java.
All right, I look it up. Java compare. Comparator. Interface comparator. Boolean equals int
I
compare.
think there's another interface called comparable.
Okay. Do I want to use comparator or comparable?
You have an example.
It depends on what you're.
Ay,
For the
caramba.
state of implementing comparable, you could create a new comparator.
All right, I'll figure this out for you on the fly in class.
On the assignment website, you use comparator as an example.
The elements are ordered using their natural ordering or by a comparator provided at set creation time. Let's do natural ordering. That sounds more natural. Interface comparable T. Okay. So I'm going to come here and I'm going to say myState implements comparable, and I have to pass the type I'm going to compare it to, which I think is a myState. I think I did that right. Now, this interface is going to have the following methods. Int compare to. So I'm going to come down here and add a int compare to function. And I'm going to compare with myState. And now I will say, if this dot x, just to be funny, let's call it that, is less than that dot x, return -1. If this dot x is more than that dot x, return 1. If this dot y is more than that dot y, return 1. I forgot. If this dot y is less than that dot y, return -1. Okay. Now that I have implemented comparable, thank you. Else, return 0. I've implemented comparable, which means I promise to provide this method. And by providing this method, I give my states an ability to compare with other my states. Now look at how I implemented this. I compared the x's and I did that, and I compared the x's and I returned positive. I didn't even think about whether this one or that one should be +1 or -1. Well, why not?
a way to differentiate.
Yeah, I don't even care. So it's got these states and it's going to put them in a tree. The thing that does matter to me is there better be some consistent ordering. I don't care if less than in the X means greater than in the tree or vice versa, but I do care that I'm consistent. If I flipped my Y less than to +1, all of a sudden weird things could happen here because it's not really comparing fairly. If we come back to my tree representation here, it needs to be able to find the node that I specified, no matter which node I specify. But how they're organized in this tree really doesn't matter. So I compared X's first and then Y's. What that means is it's as if X is the big endian value and Y is the little endian value. So essentially, if you're a little farther this way, a little farther horizontally, but you're on the same line, it's going to say that totally trumps. Whereas if you're a little far, or rather, let me say that again. Even if you're less than vertically, but if you're greater than horizontally, that greater than horizontally trumps, and then you become greater than, or possibly less than, depending on what that means. And I don't even care. You could move your Y up instead of in front of the X, and the whole thing would still work. It doesn't matter as long as you do it consistently. I do not feel I have expressed this in any type of coherent way, but if you're smart enough, you'll figure out what I mean. Ooh, that was I was then going to ask how many people understand what I mean, but now I've just realized that I've just called you dumb if you didn't. I don't mean it like that. What I mean is, I know that wasn't very comprehensible. How many people really need me to do that in a more intelligent way so that I can be a helpful teacher rather than a confusing one?
Why are we comparing X's and Y's? Shouldn't we be comparing costs if we're using the priority queue and determining which goes in the order?
Yes, you should. But we're not doing this for the priority queue, we're doing this for the tree set, because we're trying to solve the bin there question. So you're absolutely right. There is a priority queue and there is a tree set. They're two different concepts and they need to compare in different ways. So we need to talk through this and make sure that's crystal clear in your head. I think you want to clarify.
If you want to use the natural order for your tree set, you cannot use the natural order for your priority queue because they need to be sorted in different ways.
Yes.
So in one or the other, you need to use the comparator.
That's going to be true. Did you hear that? Let me state that again. Your MyState objects are going to have to go through this priority queue. When they do, they have to be sorted by their cost. They're also going to have to go in this bin there set. And when they do, they need to be sorted by their state. They're two different things. One way to do that is to use the comparable for one of them and the comparator for the other one. That's kind of confusing and weird in my opinion, but that's actually probably the really easiest way to code it up. Another way to do it is to set some kind of a flag for which way you want to do the comparison, and then actually have logic inside your comparison code that does that. Then you've got to keep that straight. So there's a little bit of nastiness as pertains to that. You could use separate comparators. So when you create a priority queue, you pass a comparator to it, and it will use that comparator when comparing. And when you create a set, you could also pass a comparator to your set, and then that would use that comparator to compare the objects. This way, in my opinion, is the most elegant, because now you're really telling it, use this one for this set, use this one for this queue, and if you had a third one, you could make a third one for it. And now we're not really hacking it anymore. So the recommended approach is use a comparator in both cases and pass it to the tree set or priority queue objects when you make them. I should have told you that moments ago, but I didn't think of it until just now. So this whole comparable thing, that's the bad way to do it. Scratch that. Shall we do it the right way now?
You have a comparator.
I'm doing my best to salvage myself here. The truth is I didn't prepare and I showed up not having really thought about this. Okay.
Look,
I confess.
look on the